Hi, I'm Joseph,
And I'm Banu.
and this is our CS-4365 project. In the past years, in the technology industry, a recent trend has shown that there's a rise of containerized systems. According to an industry study conducted just last year by Portworx and Aqua Security, the overall usage of containerized systems such as Docker was around 55% in 2017, yet jumped to around 87% in 2019. And when it actually comes to monitoring the resources these containers consume, there are many tools to choose from, such as Sysdig or C-Advisor. However, a lot of them are designed for system administrators managing Docker deployments, and because of that, they lack high granularity and low overhead. Generally, they really only have one of those two. And when we're studying Milley bottlenecks, we need both. So Milley bottlenecks are brief resource bottlenecks that propagate throughout an online system. They generally occur over relatively short intervals, maybe on the scale of tens of milliseconds, and then become amplified due to the dependencies and their effect on downstream components. So we see this example diagram on the right. We see the output statistic at the top, system response time. We see two large peaks at the top, and all the way at the bottom, we can see the root cause, which is Tomcat garbage collection on the Java JVM running and propagating those delays throughout the rest of the system. So this problem materializes as the long tail problem, which is when you have abnormally long response times, which occur for a short amount of time before the system is able to recover. Understanding the long tail problem and why it occurs is really important for companies. For example, Google reported a loss of 20% of revenue from latencies greater than 500 milliseconds. And there's been a lot of work investigating these on bare metal deployments, but we're really interested in looking into Milley bottlenecks in containerized deployments using technologies like Docker. So what Docker is it's a tool used to package applications with their process level configuration, like environment variables, as well as include dependencies alongside the application. And these units that are packaged together are called images. These are then able to be instantiated on the Docker runtime into units called containers, which are a type of lightweight virtualization. And in this, we use the host operating system's kernel while still maintaining security and isolation, which is in contrast to traditional virtualization, which is much more heavyweight. And because of this, we're able to run a lot more Docker containers and run them a lot faster. So on the right, we have an example diagram of the architecture of Docker where we have multiple application containers running on a single host. So as we were developing this project, the original goal was to adopt the WISE microblog benchmark, which has been used to study Milley bottlenecks in the past. And specifically, our goals were to containerize and orchestrate it using Docker and Kubernetes and get it working in that type of environment. So Kubernetes is an automatic deployment software tool used to create scalable systems with Docker containers. And the idea is we could adapt the WISE microblog benchmark to study how Milley bottlenecks emerge and propagate in containerized and orchestrated systems. The first step to doing this was to find a monitoring tool that would be able to provide sufficient high granularity and low overhead, yet still work with containers. So we had a wide range of tools we ended up investigating, such as Docker Stats, Sysdig, C-Advisor, and Moby.
So, as Joseph said, the two main requirements for a monitoring tool were high granularity and low overhead. High granularity is achieved through consistency and precision of collection intervals, consistency under medium and high loads, and precision of sample data collected in each interval. Low overhead is achieved through collection having a relatively low impact on application performance and a reduced amount of bias present in the final results from collection. Docker Stats was the first tool we examined. Docker Stats is a monitoring tool native to Docker, and it pulls Docker every 1 second with this fixed time interval that cannot be decremented. Due to this unmodifiable, lengthy polling interval, high granularity is not achievable, and this tool did not meet our needs. C-Advisor is a CLI tool developed by Google to aid system administrators. C-Advisor operates similar to Docker, running as a background daemon and collecting statistics on resource isolation parameters, historical resource usage, and network statistics. C-Advisor also outputs a log that provides data for all running containers. The data it includes, highlighted in blue, contains CPU stats and timestamps, which is what we're looking for. However, as highlighted in red, the output includes entries for C groups other than Docker containers, which means it is doing much more work than necessary. This excessive monitoring leads to high overhead, which we don't want in a monitoring tool. Similar to C-Advisor, Sysdig is built for system administrators and monitors fine-tuned performance of a single machine. Sysdig allowed for adjustable collection intervals with a lower limit of 100 milliseconds. We were able to bypass this limit by recompiling the binary to remove the restriction. A problem with Sysdig is that intercepting all sys calls introduces significant overhead, and this is a problem we want to avoid in a monitoring tool. Sysdig also offers a curses-based CLI tool, and here's an example of the curses-based C Sysdig output. Something we noticed during testing was that although we compiled the binary to remove the limit, it seemed like there was a hidden limit on how fine granularity could be. When passing 50 milliseconds, Sysdig collected at a 1 second interval. This, combined with the fact that it would be difficult to get data out of the pseudo GUI output, meant that we had to keep looking for a better monitoring tool. The final monitoring tool we looked at was Moby. Moby is a framework part of the core Docker engine built in Golang. Moby runs as a daemon, communicating with the Docker CLI through Unix sockets. We added a configuration option to a forked version of Moby that allowed for collection granularity and automatically started collection for running containers and saved stats to a log file. We experienced some difficulties in profiling to measure overhead. Moby also cannot be generalized to include Kubernetes metadata, and maintenance is impossible. We lose collection when Moby occasionally degrades past 1000 milliseconds. Because of these drawbacks, Moby is not a tool we could use for reliable collection.
So with all that in mind and all these tools that we've looked at, we decided that ultimately we needed to create our own custom tool, which we called Artvisor. The name's actually a play on Google's own C-Advisor tool. So the main motivation behind producing this project was to solve the shortcomings of Moby. For one, this project or the software is built in Rust, which is a low-level language similar to C, with similar performance characteristics that allow for a lower overhead. Additionally, Rust is an unmanaged language, which compared to Golang, which has a garbage collector, Rust doesn't, which means we avoid the additional overhead of garbage collection. And as we've seen, garbage collection itself can even produce short-lived resource utilization spikes that we would like to, as much as possible, avoid in our instrumentation. And the main implementation of Artvisor um, is really towards a similar functionality of Moby. It collects runtime statistics for all active containers, and it does so at specified collection intervals. To do this, we utilize a feature of Linux, the Linux kernel called cgroups, which are hierarchical groups of processes used to monitor and limit resources. Throughout the design of Artvisor, we strived to operate as efficiently as possible to ultimately reduce the runtime overhead. The way we were able to accomplish this was with Artvisor's concurrent architecture. So this is a sequence diagram that shows the structure of Artvisor. It runs in two threads that operate concurrently. On the left, in blue, you have the polling thread, which filters and sends add/remove events to the collection thread. And on the right, you have the collection thread in red, which reads cgroups and writes every time a buffer is flushed to the CSV log files. They communicate through a shared channel, which is in the middle in purple, which is a thread safe channel implemented using Rust's concurrency control features. Each thread, each one of these two threads runs a sleep loop and has a different collection or has a different sleep interval. So, for example, the polling thread has a much longer interval than the collection thread. That's because containers change much less frequently than the resource utilization that we're trying to investigate. Now we have a short demo of the functionality of Artvisor, showing us be able to start a container and be able to instrument that container and give us runtime resource utilization statistics. So for the demo, I'm just going to show off the different capabilities of Artvisor and show it work to instrument newly created Docker containers on my local machine. So what we have is we have a couple different panes. On the bottom right, we have the um, directory listing of var/log/artvisor, which is where those output logs are going to end up eventually, which is currently empty right now. Once we run it and execute Artvisor, you'll start to see that being filled up. In the right side middle, we have Docker PS, which lists the active containers, and that'll be updating as we proceed in the experiments. And then we just have two terminal prompts. So what I'm going to start doing is we'll see what the output type or output is of Artvisor when we type Artvisor help. So this gives us all the information on how we use this command. It tells us that the main subcommand is run, which we can use when we type Artvisor run. And then if we type this, it'll tell us we need a provider. So the two providers we have implemented in Artvisor currently, we have Docker and we have Kubernetes. If we type Artvisor help run, it'll tell us that. It'll say providers, containers, pods, and if we run with Docker, we shouldn't see anything happen because there are no Docker containers running. In fact, here I forgot to run it as sudo, which means that it couldn't even connect to the Docker socket. If we run it as sudo, then it's able to run, but it's not going to be doing anything. So you can see in the bottom right, there are no log files being generated. That's because there are no active containers in the system. So we can stop it, and now we'll start a container. But first, I'm gonna have it run in verbose mode so you can see the container start to be collected as it goes. So in the top right, I'm gonna paste this command in, which will start a new container and attach the current terminal. So we have the container started, and you'll notice on the left, it says identigrade cgroup fs as a cgroup driver and received a container from the Docker API. So we have this new collection target, Artvisor test, which is the name of our container here on the right. We see the container appear in the list of containers here, and we see a log file that's being generated here in the Artvisor log output. So if we end up stopping the terminal by typing exit, you notice on the right it says exited, and then on the left in our output, in verbose output, it says receive stop event. So it realized that the container was stopped and it sent a stop event across the shared collection channel. Now in the bottom right, we still have our file, which should be unchanged now that we've stopped collection. We can now go into the directory, so it's /var/log/artvisor/stats, and we can view the file. So what you'll notice is that it has first metadata at the top. It has information about the provider used, which is Docker. If it was Kubernetes, you see Kubernetes there. It says the timestamp of creation, which was exactly 1 minute ago. It has the ID of the container and has information about my system. It also then right below that has all the CSV main content, which is all tabular data. So this is very long. There are a lot of lines, too much to show, but all of these are the resource utilization statistics for our container. Of course, it didn't do very much, so they probably won't change very much since it was just in a bash terminal the entire time. But if it was doing more, then you'd see these numbers fluctuate a lot more. So that's really the main functionality of Artvisor. From a Docker perspective, its main functionality is to be able to instrument these containers, and then we're able to automate this process on Cloud Lab to attain much more useful resource utilization logs in our final experiments. So now that we've seen these two competing tools, our patched Moby and now Artvisor, we needed to figure out which performs better. Specifically, we look towards going back to our original criteria and we look to see which performs better in these two categories, which are low overhead and high granularity. The way we're actually able to do this is to look at each tool's numeric performance when it comes to different ways we can measure these criteria directly. For low overhead, that means that the tools need to have a low measurable performance impact when they're running on our systems. And for high granularity, that means that the tools need to display both consistent and low observed collection intervals that, as much as possible, approach the target interval we set. So to get these performance numbers, we created 3 different experimental configurations that run on Cloud Lab, which is an experimental testbed used for cloud computing research. 2 of them are synthetic benchmarks, and one of them is a real-world benchmark using the Wise microblog benchmark, which is a Twitter-like application that leverages microservices. So in each of these experiments, we use a purpose-built experimental matrix that lets us vary what independent variables we test. Example is the loaded instrumentation, so whether we load Moby or we load Artvisor or Collectl, or we can also vary test-specific variables. So in our 2 synthetic tests, one of the variables we varied was the peak CPU allocated towards the benchmark. On the top 2 charts, we have 50% and 100% CPU utilization that's allocated towards a benchmark, and you can clearly see how the utilization is capped there. And on the bottom 2, we have 2 different workloads that we use for the application benchmark, where we have a randomized sustained workload on the bottom left and a randomized bursty workload on the bottom right. So each test ended up having a 2x5 matrix for 10 total combinations of independent variables. On top of that, we ran 30 replicas of each experiment configuration to really just demonstrate reproducibility and obtain as much data as possible.
To run these experiments, we utilized a set of custom tooling that helped us provision, execute, and analyze our experiments. The experimental workflow scripts are bash-based scripts with SSH and SCP commands, and are used to orchestrate running benchmarks on remote cloud nodes. These scripts also transfer results consisting of log files, metadata, and configuration values back to the user. The automation scripts utilize Selenium and the experimental workflow scripts, allowing us to run hundreds of replicas automatically. The figure shows the instantiation of a project onto Cloud Lab through the automation and workflow scripts. To analyze the data, we built parsers. Python parsers allowed for us to parse log files and made it easier to aggregate the data once parsed. We aggregated and analyzed the data in Jupyter Notebooks. Jupyter Notebooks are a web-based application that allow for shared documents containing code. Notebooks also allow for iterative design and easy visualization. The figure shows us using our data to output graphs through Jupyter Notebook. And now our results. In our first two experiment types, we looked at both direct and indirect CPU overhead. By looking at the average CPU utilization for each test comparison, we saw that Artvisor had significantly less performance overhead under load, though Moby had less performance overhead than Artvisor at idle. However, this isn't as important, as performance overhead under load is a much more common and important scenario when conducting active experiments. We also looked at results for indirect CPU overhead using NBench. The benchmark produces a set of aggregate scores for memory, integer, and floating point index. Both under 50% and 100% peak CPU utilization, Artvisor performs slightly worse than Moby, though we have ideas as to why this is the case. Here we have histogram showing response time for microblog application benchmark. The graphs show the response time and frequency of requests in each response time. The graphs also show bursty and sustained response times for both Moby and Artvisor. Through the data, there is no noticeable difference in Moby and Artvisor's response times. Even though we didn't notice a difference in the distributions, we did notice the long tail phenomenon. This makes sense because our deployment configuration was very similar to the bare metal microblog deployment configuration, which has been shown to exhibit the long tail phenomenon in the past.
So now looking at the high granularity section of our criteria, we have scatter plots we've generated that graph CPU utilization rolling average versus the collection interval. For example, these tests are the direct tests at both 50% and 100% max CPU utilization. The reason we use a average for CPU utilization is because it's very prone to moving around quickly, so we want to avoid that. Otherwise, we can get our data being skewed or distorted in some ways. So we take the previous 5 entries and we compute a rolling average on that. And as you can see from the results, Artvisor, which is in red, has entries clustered very closely to the 50 millisecond target interval, and it very rarely goes above that. In fact, over the course of our 3 million collection intervals that we observed, it never even went over 100 milliseconds. On the other hand, Moby has a much wider distribution, and it's degraded past even 1000 milliseconds at times during our tests, which really just displays a long tail problem within the collection tool itself, which is really unacceptable in our workload because we lose all of the data during those degradations in collection performance, which means we're not able to analyze micro bottlenecks, Milley bottlenecks that might occur during that time. We also have scatter plots we've generated for the indirect synthetic benchmark, which show very similar distribution characteristics. Again, these both tools are configured to run at 50 milliseconds. And then lastly, for our application benchmark, although much less extreme due to the lessened CPU load, we still see Artvisor performing extremely consistently, whereas Moby, even at this low CPU utilization, still performing inconsistently. Looking towards the future, there are many ways we can improve our project for both the experimental workflow we developed and Artvisor as a tool. For the experimental workflow, we could finish our original project purpose and completely adapt the WISE microblog benchmark to Kubernetes to operate in an orchestrated environment. Now that we have a tool for instrumenting Docker containers, it's a lot easier to properly collect those statistics from the Kubernetes cluster and analyze them later. We could also test additional configuration options to expand the experimental matrix. An example of that is testing different collection intervals to examine the relationship between the observed collection intervals and the target collection intervals for different combinations of tools. Finally, we could also improve the synchronization control in the experimental workflow scripts so that they're more consistent across all the different result replicas. And then looking at Artvisor, there's also a large amount of potential features we could add. One of the most important of those would be to reduce the performance overhead seen in the polling thread, either by using a lightweight HTTP client to replace our heavyweight Docker API bindings, or to just take the shortcut of listing the directory in the C groups of the Docker parent C group. Either way, we'll be able to reduce the overhead that the polling interval or polling thread creates, and hopefully reduce the overall runtime of the tool, maybe allowing us to prevent what we saw with the nbench benchmark where Moby outperformed Artvisor. There's also a want to implement Windows support for Artvisor. So since Windows added first-class supports for containers in the host compute services API, we could now make it so that Artvisor was able to instrument Windows containers, making just a more versatile tool in general.
Through our project, we investigated several monitoring tools, such as Sysdig, CAdvisor, and Moby. Due to the shortcomings of these tools, we developed Artvisor. Artvisor achieved both high granularity and low overhead, and never degraded past 100 milliseconds in all 3 million collection samples. We hope Artvisor will be used in the future to detect the occurrence of Milley bottlenecks in containerized and orchestrated systems.